Okay, this week on the Fungineering podcast, we are finally going to talk about the Space Shuttle Columbia disaster.
Finally.
Finally, it's been many, many months to get this recorded. So, the Space Shuttle Columbia crashed in early 2003 with a loss of all 7 people on board.
Mm-hmm.
It was the second shuttle that was lost. And afterwards, the shuttle fleet only had 3 vehicles left, but they still managed to complete a somewhat truncated manifest of shuttle missions, even with 3 remaining vehicles. Ultimately, at a high level, the cause of this accident was foam shedding from the external tank that would damage the thermal protection system on the left wing and then cause the shuttle to break up upon re-entry. But there's a much more interesting story here before and during and, of course, after. And unlike the Challenger story, this is less interesting from just a pure engineering analysis standpoint. And it's more interesting from the cultural standpoint of NASA and the people involved and what NASA seemed to have learned, at least on a short-term basis. And we give NASA a lot of crap about this, about, NASA didn't learn anything from Challenger. And, in NASA's defense, I think it's important to point out, when we say NASA, it's not this monolithic, unchanging, static organization of people who never age and go through time from Apollo to today as the same people. It's many tens of thousands of civil servants and contractors who have some turnover rate in their structure every year. And so just like any organization, some lessons are lost over time. Now, NASA does have a lot of other problems that encourage it to forget lessons, but it's not entirely fair to blame it all on NASA, just most of it.
I think I'll keep blaming all of NASA.
Okay, you can do that. I'll just blame them for most of it.
Okay.
Through the late 90s, from 1992 through the late 90s and the early 2000s, there was an administrator at NASA who had this great idea. And basically it was, let's do everything better, faster, and cheaper, which maybe you've had the misfortune of encountering this at a place you've worked, where they want everything to be higher quality and done quicker and for less cost. And of course, if we think about this rationally, you can get 2 of those by sacrificing the third, of course. If you cut quality, you will produce everything quicker and at lower cost, and the other 2 combinations too. But there was this delusion from the very top at NASA through most of the 1990s that we need to push all 3 of these things. And, we'll just succeed somehow. It'll just happen because we'll print up enough motivational posters. We'll have enough talking points at the beginning of useless meetings all over the space centers. And eventually this will become ingrained and will solve an intractable problem. And we will accomplish better, faster, and cheaper. And of course, it didn't work. And ultimately, one of the problems was that the program manager for the space shuttle was simultaneously responsible for cost, schedule, and accomplishing the mission. So he was responsible for the better, the faster, and the cheaper. And he needed to rationally, as an engineer, make sacrifices and make compromises in accomplishing 1 or 2 of these goals, or maybe all 3 at slightly less than what was desired that they should increase by. But you had one person. You didn't have this responsibility where you had maybe a guy who was in charge of finding ways to cut costs, and he was checked and balanced by another guy who was in charge of increasing mission success and accomplishing more on each mission and this kind of thing. So there was this kind of impossible task given to the director of the shuttle program.
If they had used the 3-person triad of better, faster, cheaper, would that have even made a difference, though? I don't see how that would.
I think you could get more ideas. You would, if nothing else, you would have 3 stakeholders who might eventually come to the conclusion that this is not working. Maybe we should go to the administrator. Instead, you had one guy who was the director of the shuttle program, and he said, and I don't mean this in a bad way. He said, "Look, I've achieved the pinnacle of my career. I am the director of the space shuttle program for NASA. Now, what can I do to not screw this up?"
Mm.
And certainly he's going to do, and likely the people who get into that role are highly ambitious, highly capable. And so they're going to give their best shot at it. But when they're one person, you're not going to have this struggle between multiple people who all have their own best interests and who might rationally come to the conclusion that this is an impossible goal.
Okay. I feel like if you built the better, faster, cheaper triumvirate of engineers, almost ironically, what would happen is it would cost more because you're employing 3 engineers. It would take longer to build everything because now you have a committee of 3 people. And because they're all fighting over the 3 different outputs, you would probably produce a lower quality product.
Well, maybe NASA was fucked no matter what. But ultimately, the fucking came from the administrator down.
All right.
Okay. And so we go into this era in the early 2000s, and the shuttle program is marching along. And there was a recurrence of the problem that had caused the Challenger accident, and that was the normalization of risk. And it was that NASA would see a problem, they would see a failure of a system on the space shuttle, and they would say, well, that failure didn't cause anyone to die. We didn't lose a shuttle. We didn't lose a mission. So it's okay. Apparently, we can go into that space and come out of it okay. And so now they would say that going into that space was a-okay. We don't need to worry about it. And so over time, the amount of danger they were undertaking with the shuttle program would just increase and increase and creep along. And this culminated then in the Columbia accident. So when Columbia launched, it was on ascent and a piece of foam broke off of the external tank. So there's all this foam around it that insulates the tank because the tank has cryogenic oxygen and hydrogen in it. And you have to try and keep it warm so too much of it doesn't boil off while it's sitting on the launch pad. And
actually, I would like to describe that a little bit more in case people have a little trouble visualizing the shuttle stack. So the shuttle is the little airplane thing that sits on the side. And then there's the big brown tube. And that's the external fuel tank. That's the thing. And the reason that thing is brown is because it's covered in that insulation. And then the 2 white missile-looking things on the side, those are the SRBs, and they don't matter for this accident. In case you have trouble visualizing this.
Yeah, and if you really don't know what it is, just go to Google and type in space shuttle and look at the images, and you'll see this big orangish brown tank thing underneath the belly of the orbiter.
Yeah, that thing's not a rocket.
Yeah, that's just a fuel tank. It's not a rocket. That's correct. It would just pump fuel into the space shuttle, and then the 3 engines on the back of the space shuttle would burn that fuel on ascent. And so it had this foam on it, and foam shedding was a known problem. So there had been foam shedding events throughout the shuttle program for almost 20 years. And foam shedding causing damage to the thermal protection system was a known problem. And again, it had happened for almost 20 years. And NASA over time had normalized the risk of it. And so I guess we should talk about this thermal protection system a bit. When the shuttle re-enters and comes back into the atmosphere, it decelerates and it descends to land at the end of a mission. There's a lot of heat generated because it has to slow down, and it slows down by very gracefully hitting the atmosphere and dissipating its speed. And all this heat that's generated, though, can't be allowed to destroy the shuttle. So it has basically a 3-part thermal protection system. The first part that you probably know, if you're over about 30 years old, is the tiles. And so they're these, I think they're silicon-based tiles of some type, and they're very lightweight. They contain mostly air. And there's something like 30,000 of these tiles on the bottom of the orbiter. And there are demonstrations you can go look at on YouTube where a guy will hold one of these tiles in his bare hand, and then he'll hold like an oxyacetylene torch, and he'll have the torch burning the top of the tile while he's holding this, 2 or 3 inch thick tile in his bare hand. And of course, none of the heat comes through the tile to burn his hand. So they're very good insulators. Those tiles were mostly used on the bottom of the orbiter. Around the leading edges, you had what was called reinforced carbon-carbon. And this is a carbon fiber that is used to reinforce a graphene structure. And so it's a very complicated method to produce this, and it's very expensive. The price estimate I saw was that it cost about $100,000 per square foot to produce it, because of the combination of the difficult manufacturing method and the complex geometries that were used on the space shuttle. But it's used on the leading edge because I believe it's because of the type of aerodynamic forces that the leading edge sees that the belly does not see. And then the third type of thermal protection are thermal blankets. And they are just kind of cheesy blankets, but they're used in spots where during reentry, you don't have high aerodynamic loading. And so it can just be a completely non-structural blanket, and the little bit of heat that it sees will be prevented from damaging the orbiter, and it doesn't see enough airflow to rip the blanket off. So that's the 3-part thermal protection system. So on ascent, you have this shuttle stack flying really fast. It's accelerating the whole way up. And this piece of foam broke off. And it hit the wing. So it hit the left wing, and it hit one of these reinforced carbon-carbon panels. Now, they have video of this from the ground. And I believe this was one of the first missions where they had video from the air also, but it was not good high-def video, and it wasn't very high frame rate. And so the engineers, as usual, would start analyzing the ascent footage after the shuttle was launched, and they would look for foam shedding and look for other anomalies. And immediately they see this large piece of foam that broke off and hit the wing, and they could tell it hit the wing because it turns into a cloud of foam after it hits. But the specific moment when it hits the wing was in between frames on the video, and so they could not see exactly where it hit. They could make estimates. So this space shuttle mission was not going to the space station. It was a science mission that was just going into orbit and doing a bunch of whatever they would do on the shuttle and then come home. Now, because of that, they did not have a convenient way to look at their own wing leading edge. And it sounds really weird, but if you're inside the space shuttle, you cannot look out a window and see the wings. Additionally, the robotic arm on the shuttle that could have been used to just look out, it has several cameras mounted on it. It was not installed on that mission because they had no payload that they needed to move around, so they didn't take a robotic arm with them. So they could not just pick the robotic arm up, maneuver it out over the side to look at the potential damage. So there was no way to see it easily. They would have had to send a person spacewalking out to look. And there was actually a procedure for getting down the wing, and there were procedures for getting underneath the orbiter too, which is really interesting because I don't know what they were supposed to hold on to. Yeah, Blake's giving me a weird look. Yeah.
I can't imagine. Did they bring an MMU with them?
Untethered flights were long banned by this point.
Okay.
The MMU is the something mobility unit. I forget.
Manned maneuvering unit.
Okay, manned maneuvering unit. It's this big backpack looking thing that you'll see the astronauts wearing on spacewalks. Basically, it's like this cool little jetpack that can fly you around. And they did some tests early on in the shuttle program where they would have a guy like and I don't know how many times they did this, but there is one famous photo of an astronaut spacewalking, and he looks to be like a quarter mile away from the space shuttle, just floating out in space. And so it was initially intended as a way to just maneuver around in orbit when you're outside of the shuttle. And then maybe rationally, NASA lost its nerve and said, we're not going to have guys just flying around with this thing, because basically if it breaks, there's no guarantee that we could catch them. And so by 2003, when the Columbia was lost, this was far past the point where NASA would not allow untethered spacewalks with an MMU. And yeah, I'm similarly perplexed about how they had a procedure to crawl under the orbiter and what they would hold on to, because
system of straps.
All of my experience when I was working on the shuttle program, and I worked on the shuttle remote manipulator system, the arm itself, I did engineering on that for 4 years. All of the experience of spacewalks that I watched and everything during that time, it's hand over hand crawling down International Space Station structure, where there are intentional attachment points every so often, and you can slide a safety cord that you have tethered onto the station. And the whole space station was built like that, so you could spacewalk safely all over it and be tethered to it 100% of the time. So yeah, I'm confused about it too. Maybe somebody who knows, some former NASA person who understands how the procedure to get under the shuttle worked, will come on to Reddit and tell us.
Yes, please tell us.
We're dying to know. So they did apparently have a procedure they could have crawled under if they had wanted to. And here's where the story gets kind of upsetting and kind of sad and unfortunate. So there were these engineers at NASA, and principal among them was a man named Rodney Rocha. And Rodney Rocha at the time was the chief engineer of the structural engineering division at NASA. And he had been at NASA for quite a long time. There's a story I read about him working on Columbia while it was being built in the 80s. And I'm sure he predates that a bit too. He looked at this footage of the foam hitting the wing, and he was very concerned about it. It was a very large piece of foam. It's been described as a suitcase-size piece of foam. And NASA had a essentially spreadsheet table that could model foam impacts. And there were a lot of problems with it. There was very little data to validate the model. There were several shortcomings of it. And they plugged in what they could assume from the limited imagery that they had of the foam strike, and kind of various things I've read have said, well, it underestimated, it overestimated. They couldn't really be sure. Basically, they didn't have enough faith in that model. And so Rodney Rocha, among some other engineers there, started to push the mission management team to get images of the wing. And so he asked, could somebody just look out the side hatch? Because there is a hatch on the left side. It was the left wing that was struck, but you can't see the wing from the small porthole in that hatch. He said, what about we go to, I would assume, the National Reconnaissance Office and say, hey, let's get a spy satellite to look at the shuttle and just make some images. And apparently this was a thing that had been talked about before at NASA. I'm not sure if it had ever been done before, but there were connections from NASA to the intelligence community where NASA could at least request these images and probably expect to get them if it asked. And when he and these other engineers took these requests to the mission management team, they were again and again shut down. As I was doing research about this, an interesting thing was happening over and over. There was this pervasive attitude that even if there is catastrophic damage to this wing, there's nothing we can do about it. And there's a story about a conversation he had with another engineer I believe he was trying to convince this other engineer to help him, get some leverage on the mission management team, come support him. And basically the conversation ended with the other guy saying, look, even if the damage is terrible, all we're going to do by going and looking at it is tell the astronauts that they're going to die on re-entry. And so we shouldn't even bother. And he encountered this attitude from many people inside NASA. There was one mission manager named Linda Ham who was kind of in charge of this mission. And she was, at least in the reading, she is kind of blamed the most for resisting his efforts. And it's interesting because Linda Ham, she was actually married to a shuttle pilot at the time. They got divorced later. So Rodney Rocha tries for many days. And of course, the shuttle mission was about 10 to 14 days long in this time period. And so he tries for many days to see if he can convince these managers at NASA to ask the intelligence community to take images of the wing. And finally, they just basically tell him to go take a hike. They're not going to do it no matter what.
Do you think that they could?
That's an interesting question. Would they have a satellite that had a focal length that could hit the shuttle, that could track it?
Right.
That could, you know what? I'm going to say, I bet there are enough intelligent people that they could have said, look, at some point, the distance between the shuttle and the satellite will be the same as the distance between the satellite and the ground. And we can attempt this. It may take several passes to get it right, to get the timing right for the exposure. I think they could have done it.
I don't think so. Because say you wait for the distance to be the same. It's going to be the same for a fraction of a second, maybe a frame. And I don't think the NRO would set up their satellites to be really high frame rate because there's little point to it. Like, they're trying to take really detailed pictures of the ground at a fixed distance. I guess they're not fixed distance because the orbits do vary in distance from the Earth. But I would expect their cameras to be set up to always be taking a picture at that distance. Like, it would be hard to manually adjust the focus. And they wouldn't be high frame rate. And they wouldn't be able to track a tiny moving target. I would almost expect that if you were to ask the NRO to take pictures of the shuttle, and they could do it, they would be like, flip it over, take pictures from the ground.
Yeah.
Because I bet they have better telescopes on the ground for looking at foreign satellites than they do have spy satellites for looking at not the ground.
And these requests for imagery also potentially included using ground assets. Now, I would doubt Rodney Rocha is an expert in satellite optics and telescope optics. He was simply asking, somebody get me a picture. In the same way we ask experts to do so many things. We say, you're the expert. This is what I need. You figure out how to do it. And so I think he would have gotten a picture from somewhere.
Maybe. I could also see them not wanting to say whether they could or could not get a picture.
Of course. Well, and what they probably would have done is just classified the photo and read everybody in. And
yeah, okay.
And then just brought the photo. I mean, when I was at NASA, I guess 2006 to 2010, there were still like rooms that were black where they kept the secret stuff from the classified DoD shuttle missions from the mid-'80s. So they still had like some black stuff that was stored there. And you still can't get video imagery of those missions. Even the launch video is still classified. So NASA does have some capability to handle classified materials. So if some government agency had said we acquired a picture somehow, there was some infrastructure already in place for NASA to host that image and keep it classified and potentially distribute the information from that image correctly in a classified way.
Okay, sure.
I think they could have handled that.
Yeah, I think you're right.
So ultimately, Rodney Rocha's efforts to get the imagery were shut down. And he lived in Clear Lake area because he worked at Johnson Space Center. So the Saturday morning that the shuttle was going to land, he drove in to Mission Control, and he was in one of the rooms observing on the TVs and watching telemetry data during the reentry. And everything was going nominally until some signals started to be lost. There were anomalous signal losses. And so you might expect that a certain sensor might fail, or, a certain electrical bus that hosts a bunch of different sensors might fail, and thus all the sensors on that bus fail. But sensors were failing in odd ways. For instance, all of the tire pressure sensors on the left landing gear tires were suddenly lost at once. And you would expect that those should be wired on different circuit breakers so that one circuit breaker blowing doesn't lose all your sensors. And you should expect that 3 or 4, however many they had, would not all simultaneously fail for different reasons. And yet they're all lost at once. And so these kind of anomalous things start happening, and they're happening during a period of flight where communication with the shuttle due to the re-entry is basically broken up for a few minutes. It's difficult to communicate with them over radio. And eventually Rodney Rocha is kind of observing this from one of the back rooms in Mission Control, and they learn, I believe Mission Control learned first through a phone call from a mission controller's wife who was watching the reentry on CNN, and CNN was seeing that the orbiter was breaking up, and she called her husband, and then he told the flight director that the shuttle had broken up. And Rodney Rocha was there in Mission Control as it happened in the back room. So immediately the investigation starts to focus in on this shed foam. And it doesn't take very long as they start examining the debris field, which stretched across East Texas and West Louisiana. They start looking at where different parts fell. They start looking at what assemblies came apart. And it was very easy for this investigation to establish that, yeah, it was this hole in the wing caused by this foam. And so they went back and they examined what is the susceptibility of the reinforced carbon-carbon panels to foam traveling at the velocities that it would have been traveling at this regime of the ascent when it was hit. So they set up this test stand where they would fire a piece of foam out of an air cannon at a piece of reinforced carbon-carbon that was on a frame that was shaped approximately the same way as the wing leading edge. And they did several tests of it over a number of days. And one of the tests, they ended up with a gap in the panel, basically a busted out hole in the reinforced carbon-carbon panel that was approximately 16 inches by 16 inches square. And so during re-entry, you have all these hot gases that are basically compressed by your orbiter falling on them. And they flow up around the front edge of the wing. And when you have this huge hole in the wing, those hot gases start to come into the wing. And that's why you started seeing these sensor failures. The gases were basically melting the structure inside the wing and destroying everything. So as the orbiter started to have this happen, it performed as it should have. So let me take a little detour here, and I'll get into a concept called control mixing, which is this thing in aircraft where you have multiple flight regimes for an aircraft, but you want your pilots to have basically one set of controls that they use. And so the computer on the aircraft will take the control inputs from the pilot, and it'll say, well, let me think about what type of flight I'm in, and I'll decide what control surface or what actuator or what swash plate or, whatever, depending on the aircraft is. I'll decide, the computer, that is, will decide what to do in response to move the aircraft. So there are only 3 aircraft I can think of that employ control mixing, but I bet that's not all of them. the space shuttle did, the V-22 does, and the F-35B. And so I guess by extension, other like derivative and previous forms of those aircraft. So like the XV-15, which was an early tilt rotor, and like the AV-8B Harrier, which was basically what the F-35B is replacing. But in all three of these aircraft, you have radically different types of flight. You don't simply have one type of flight, like say a jet fighter that simply flies forward and creates translational lift over its wings. Instead, an F-35B can fly like that, but it can also just lift up into a hover from standing still on the ground and hover around at low altitude. And if you imagine the pilot, when he's flying like that, he's using the same stick, whether he's flying in that hover mode or he's flying as an airplane, but he's getting different outputs from the aircraft in order to accomplish those two different things. And that idea of having the controls do that is called control mixing. In the space shuttle, the way it manifested was that you would have a control system for flying the space shuttle as a glider in the atmosphere, which is how it landed at the end of a mission. And you would have a separate control system for flying in the vacuum of space, where obviously all of your glider control surfaces don't do anything because there's no air to deflect. And so that second control system on the space shuttle was called the reaction control system. And it was these nozzles placed all around the space shuttle that pointed in a bunch of different directions. And they used a hydrazine fuel, and a valve would open, mixing the two hydrazine components, and the resulting expansion of gas would be blown out of this valve. And basically it would create a jet of gas that, you know, through conservation of linear momentum would move the shuttle some way. And so you would use this on orbit for keeping your attitude a certain way or for changing your velocity. During re-entry, these RCS jets would go through a phase where they were active as well as the control surfaces being active. And so as you're descending through the atmosphere and the atmosphere is getting thicker and thicker, your normal glider control surfaces are gaining authority because the atmosphere is getting thicker and there's more gas for them to push against to maneuver the orbiter. And at the same time, your reaction control system thrusters are getting weaker because there's more gas that they have to push against. So when the hydrazine fuel comes out of them, and they're pushing against a thicker and thicker amount of gas. So if you could imagine, like if you get a mouthful of water and a drinking straw, and you sit and you just blow the water out as hard as you can. Let's dye the water black so you can see what's happening. You dye the water black and you blow the water out of the straw as hard as you can. You can make it go several feet, maybe 4 or 5 feet. But now if you get at the bottom of a 10-foot swimming pool with your mouth full of water dyed black and you blow it out of your straw, it's only going to go a foot or two because it has all this higher pressure water to push against instead of the thin gas. And that's the same reason the reaction control system on the shuttle would lose authority and lose the capability to control the orientation of the vehicle as it descended through the atmosphere. But at the same time, the regular control surfaces are taking over.
Isn't it really more because there's a bunch of air on the other side of the shuttle?
What do you mean by other side?
Well, like a rocket doesn't perform that much worse in atmosphere versus vacuum. It's different, and it'll have the wrong shape of nozzle for it, but it'll still perform. But when you're, like, say, trying to push the shuttle over to the right with the left side thrusters, the thing that's stopping you is that there's a bunch of air on the right side of the shuttle, and you're trying to push against that instead of pushing against the vacuum of space. It's that the atmosphere is gaining authority to prevent the shuttle from using its RCS thrusters to move.
Yeah, that's a component too. That makes sense.
Okay.
Do you think that's the only component?
No, I just think that the RCS thrusters losing thrust due to being in atmosphere is not that important. It's that the shuttle is in atmosphere. And so pushing the shuttle around is much more difficult. Like, to use your straw analogy, if you squirt a bunch of water out of the straw, it pushes your head backwards a little. But if you do it in a pool, it pushes your head backwards a lot less because there's water pushing on the other side of your head instead of air.
Mm-hmm. Okay, so my counter to that, which I cannot fully articulate, is from introductory thermodynamics, where you talk about gases expanding into a vacuum and how much work they do. And you treat that differently when a gas expands into a vacuum than when it expands into another fluid.
Mm-hmm.
Like it's treated entirely different, and it's not because there's gas on the other side resisting your motion, which is definitely a component and would definitely cause the RCS system on the shuttle to have less authority as you descended deeper into atmosphere.
Mm-hmm.
We're just splitting hairs on which one of these effects is the most important.
Anyway, the rockets work, whatever.
Yeah, so yeah. It's not all faked on a soundstage. So as this gas is leaking into the wing through this hole, it's basically acting as a giant brake on the left wing. And so the vehicle would start to yaw to the left. And as it does this, the computer on the orbiter says, oh man, I'm suddenly turning to the left for no reason. The pilot's not telling me to do this. And my descent profile is not saying I should do this. So the orbiter started to resist, and it resisted as it could with its control surfaces and with the reaction control system. And eventually it maxed out the authority of the reaction control system. So basically the nozzles that were positioned in a way to resist this yawing motion were open fully continuously. So they were trying as hard as they could and still not applying enough force to arrest this yaw motion. And so eventually the wing is completely compromised to the point that the hydraulic system fails. Now, the space shuttle had, I believe, 4 equivalent hydraulic systems. And this is common in aircraft. They'll commonly have 2 or 3 or 4 hydraulic systems. And basically, they're redundant to each other. And so each system is run by a different hydraulic pump. It has a different reservoir. And it's done this way so that if one system fails, one system gets a leak somewhere, you have redundant systems that can still move your control surfaces. They can still do things like open the landing gear door and do all the other things that you use hydraulics for on your vehicle. The fatal flaw to the hydraulic systems on the shuttle and most aircraft is that when engineers design these hydraulic systems, they will run all the systems, 2 or 3 or 4 of them, depending on the aircraft, parallel to each other. They all take the same path around the aircraft. And so as soon as this hot gas got deep enough in the wing to compromise the hydraulic system, it nearly simultaneously compromised all 4 of them, because all 4 are running right on top of each other all around the aircraft. And it's a terrible way to build aircraft, but I can tell you, aircraft are still being designed and built that way today, with hydraulic systems that run parallel all over the aircraft.
What do you think they should do? I mean, it's easy to say not parallel, but where do you put the lines then?
You take separate paths. When you have to go through a bulkhead, you go through it different places instead of all 3 going through the same penetration through a bulkhead. Eventually, they have to come together at the pump and at each device that they power and all that stuff. They have to get close to each other, very close, maybe parallel at those points. But where it can be avoided, it should be. So that when you have a physical penetration of the vehicle that severs a hydraulic system, you do not lose all of them.
I feel like I would give a lot of credit to the engineers that came before and say, I am sure that they thought of this. And I know there's that one famous plane sort of crash where 3 parallel lines were severed all at the same time. And so people are aware of this being an issue. But I think a lot of times it's like, what else are you going to do? If you run the lines through different holes, you're creating different holes in different bulkheads, you're increasing the complexity of the vehicle. You make the lines physically longer, which requires more hydraulic fluid, and it makes them weigh more, and it increases the potential area for faults. It just seems like the trade-offs maybe aren't worth it. You just say, yeah, if 4 lines get cut, we're dead. But what else were we going to do? I don't think that's as stupid as you're making it sound. I think it's probably the right compromise.
Do you think an argument can be made that on something like a high production volume commercial vehicle, it's reasonable to run them parallel, but on something that encounters essentially a lifetime of test flights like the space shuttle, that we should go ahead and make the effort and do this the better way, even though we make compromises? Because the space shuttle was never intended to be a commercial vehicle that would have to have a profit margin and compete in a marketplace like a Boeing passenger aircraft is. You know, on a Boeing passenger aircraft, yeah, that extra weight, that's fuel every time they take off and land at an airport, thousands of times in every vehicle's life over a fleet of thousands of vehicles. And that's a significant thing. And maybe it's not worth it because a passenger aircraft is unlikely to encounter environments where the fuselage is catastrophically compromised.
Yeah. I'm just imagining a meeting of engineers, like, where do we lay out the hydraulic lines in the shuttle? And how many should we have? And they're like, all right, how about, like, and young Craig shows up, and you're bright-eyed because your soul hasn't been crushed by NASA yet, and you're like, I say we run the lines all over the place. We have some on the outside of the shuttle, you know, we just have them everywhere. And they're like, why do you want to do that? And you're like, well, I think in case we have a catastrophic failure of some part of the vehicle, all the lines shouldn't be parallel or they can get severed. And they're like, okay, all you senior engineers in this room who are like 55, do you know how to build a system like that? And they're like, not really. No one's ever done it before. Even on commercial aircraft, they just put them parallel. And it's like, why don't we just go with the devil we know? Why don't we put all our eggs in one basket and then just watch that basket really closely? And so they're like, we're going to use more durable hydraulic lines than we expected. We're going to have better failover systems, but we're still just going to run them parallel. And then you walk out of that meeting and you're like, my soul's been crushed a little bit today. I feel like that's probably about how it would go.
Apparently that is how it goes. Because like I said, aircraft are still being designed like that today.
Yeah.
I think it's dumb, and I don't think it's as big of an issue as you think. Aircraft have hydraulic reservoirs already. So if you have more lines and you have more volume in the lines, you just make the reservoir smaller so you don't gain any weight from extra fluid. There's already penetrations and bulkheads all over the place to save weight. Go through there, you know?
You might be right. Maybe some aircraft designers are going to come post on the Reddit and tell us the right answer.
I would love to hear from somebody who designs hydraulics for Boeing or Lockheed or Airbus. You know, one of the big commercial, well, Lockheed's not a commercial maker, but, you know, tell us why this is done this way or why not, or actually, is this actually a contentious issue?
Actually, I'd love to know if it's done differently on military aircraft. They would care a lot more about catastrophic damage through a hydraulic line.
Yeah, I would love to see the hydraulic layout for an A-10.
Yeah.
So, anyway, they lost all 4 hydraulic systems at once. At which point, you're really screwed because the hydraulic systems power all your control surfaces that allow you to steer the shuttle in the atmosphere. At that point, the shuttle started this kind of gyration because it would kind of turn to a side a little bit and then be buffeted by extra load and it would turn back. And so it started this very regular periodic gyration until the amplitude of the gyration got so high that the shuttle was too far out of attitude and it started to break up catastrophically. There were several people on the ground who were filming the re-entry. They lived along the re-entry path and they would normally see space shuttles re-entering. And so there were enthusiasts on the ground who would just come out and film it with their home camera. Now, this is back in 2003 before everybody had high-def handheld cameras. So what you got were a lot of old home videotape quality videos. But the analysis of the imagery from those videos still yielded a lot of good information to the investigation. They were able to reconstruct from videos taken at different angles and from different places what sequence approximately the orbiter broke up in. And then they paired that with ballistic analysis of the debris field. So they might find some piece in the debris field that was of approximately spherical or cubic shape. And they would have a really good idea how that might fall if you iterate backwards, making assumptions about the height and speed that it was shed at. And so through this long iterative analysis of the ballistics of the debris field and the camera footage, they were able to very confidently reconstruct the order in which the shuttle broke up. Ultimately, it was not survivable at all. The orbiter was at, I believe, 180,000 feet altitude and Mach 15 at the time that it broke up. So it was completely not survivable by a space shuttle. I mean, we could probably build a vehicle with a type of escape system that could survive it, but the space shuttle was not survivable in this kind of crash.
It would have to have like a little Apollo module in it. That
yeah.
Then the shuttle would be shed from that, and then that module would come in.
Have you ever seen the escape system for the SR-71?
No.
It basically just sheds the entire cockpit.
And the cockpit is designed to be able to withstand that.
Yeah, and it's of an aerodynamically stable shape. The SR-71 was this spy plane that we built, I believe, in the 70s, and it was designed to just fly very high, like 70, 80,000 feet, and at Mach 3 or so, I believe was its max speed. And so you can imagine if you're at 80,000 feet going Mach 3, you can't exactly eject from an airplane into the wind stream.
Yeah.
And so they needed a way for a crew to eject safely. And that way is essentially the entire cockpit is this like bubble or bathtub or something that all explosively separates from the rest of the vehicle, but is itself very strong and able to then descend and deploy a parachute. Or maybe they would then do a second stage ejection from that. I don't know.
Yeah. Although if you're going Mach 15, you still got a lot of slowing down to do.
Yes. And you'll still gain a lot of heat during that slowing down.
Yeah.
When they recovered parts of the astronauts, though, basically they were recovering parts that were pretty small. An article I read had interviews with people who had found parts of the astronauts, and they were recovering like individual hands and shins, and they recovered like half of a torso was the biggest piece that anybody would talk about recovering. So the force of the breakup of the vehicle at those speeds, and then the further descent through the atmosphere and the deceleration, everything else was, it was completely catastrophic. And it essentially tore the helmets off of their heads. They would find the helmets separate from the heads. They would find pieces of clothes separate from the bodies. So, and that even happens in a lot of commercial aircraft accidents where the vehicle breaks up at altitude at just commercial aircraft speeds and altitudes, 35,000 feet and 600 knots or so. They'll find bodies that are naked because the wind has essentially ripped the clothes off the bodies. But the astronauts in this case were in much worse shape. So it was completely unsurvivable.
What if they had kept all their 4 hydraulic lines together, though? You think they could have survived? I'm just kidding. There's no way. I know there's no way.
Yeah, I mean, the wing
failed.
The wing would have still been lost at some point, and then the failure would have just progressed further inward to the body of the shuttle until eventually it became so aerodynamically unstable that it couldn't fly and it would rip apart no matter what. I know you're being facetious. I know that, but our listeners might not know that. So I do want to give that like a serious answer, even though I know you're just being an ass. But
they would have been like, thanks, Craig. You bought us a few seconds.
Yeah. I mean, yeah, it wouldn't have done much.
Yeah.
But, on the other hand, it's potentially not as tragic as Challenger was, where the astronauts were maybe conscious all the way to the ocean.
Wouldn't these astronauts have known once they lost sensors, it would have started beeping at them a lot, and they would have been like...
Yeah, so I believe that interval was about 20 or 30 seconds, where they would have known something catastrophic was happening, and the vehicle had not yet had its disintegration, essentially. And so there was evidence of that too, because the communications with the orbiter were lost at some point, and it was 10 or 15 or 20 seconds before what they termed the catastrophic event, which was the big breakup of the orbiter. And in that time interval from the last data that was sent down from the shuttle and the time that it broke up, there were switches in the cockpit that were thrown, because the switches, when they were recovered on the ground, were in a different position than the last data said they should be. Mm. So they knew that, the astronauts were still in there consciously trying to do something to remedy the situation. Essentially, the pilot and co-pilot were trying to. Probably fully aware that things were going very south and maybe were not recoverable. Who knows when each of them decided that. But so there was an interval in there for them to contemplate that. But nowhere near the amount of time that the Challenger astronauts potentially faced.
Yeah.
One of the big recommendations that came out of this, though, was that NASA published this crew survivability report in 2008, where it talked a lot about the sequence of events that led to the deaths of the astronauts, and how can we design spacecraft in the future to avoid this stuff. And of course, one of the recommendations is there should be no survival system that has to actively be turned on by an astronaut during a disaster, which NASA was still relying on breathing packs and things of those sorts that it had back during Challenger and during Columbia too. And so, space vehicles come apart very quickly. Things go bad very fast.
Yeah.
And there are examples from the Russian space program too. There was one where 3 astronauts were in some kind of capsule, probably a Soyuz of some generation, and they were re-entering and they all asphyxiated because there was an open valve, and they didn't have a lot of time to fix that. And the valve didn't have a sensor that said, hey, cabin pressure is dropping, I'm just going to try to close myself. They had to manually try to reach under the seat to close this valve to keep the cabin pressure from leaking out. And they're all strapped into their seat, decelerating into the seat. So this crew survivability report is real interesting if you want to go read that. It's about 400 pages long, but it's pretty good. I say that, but it is really interesting. I think it's neat. So NASA did learn, at least at the time, from this. Now, will that knowledge carry into the future? It mostly did not from Challenger to Columbia. And whether it will from Columbia to whatever eventually follows and whatever the next disaster is unknown, I guess. When I was at NASA, the one project I worked on the most was kind of something that came out of what was learned from the loss of Columbia. I worked on something it was a shuttle mission called STS-400. And essentially, it was to be a rescue mission in the case that the STS-125 mission to service the Hubble Space Telescope ran into a problem, probably with its thermal protective system. So after Columbia was lost, they said, look, we can only do missions to the space station from now on, because if there's a problem like this again, we need to basically have everybody just hang out at the space station until we can come rescue them. Which would have been a great plan. The space station had plenty of resources on it to support a bunch of people for a while. And the contingency plan in that case, if you were at the space station, is as soon as they knew there was a problem, 3 of the 6 people who were long-term residents at the station would get in one of the Soyuz capsules that was always docked there, and they would leave immediately so they wouldn't consume a bunch of resources. And then the shuttle would come along in a couple days and it would dock at the station, and the 7 astronauts would get out, and the 3 long-term station residents would still be there. And you'd have 10 people there on the station hanging out for a while until they got another shuttle ready, and they launched up and rendezvoused and basically brought home a bunch of people at once. And it was all a very good plan. It would have likely succeeded. STS-125 was different because it was decided that we absolutely needed another Hubble Space Telescope servicing mission. I believe this was the fourth one. It might have been the fifth, but I think it was the fourth. And the Hubble Space Telescope orbits the Earth at a different inclination than the ISS does. And because of the difference in inclination, you cannot go into orbit with the intent of catching the space telescope and then decide, I'm just going to hop on over. I'm just going to translate over to the space station. It requires way too much change in velocity to change your inclination enough to catch the space station. So the space shuttle was not going to be able, in any emergency, to be able to reach the space station and just use that as a safe harbor until things could be worked out.
So you're saying it's not at all like that movie Gravity, where you can just hop between different on-orbit space vehicles.
Yeah. How do they say, some people don't think science be like it is, but it do?
Yeah.
So it doesn't work like the movies. But we needed to service the Hubble Space Telescope, or it was decided that it would be serviced. And so they had to have a plan for, what if we get another giant hole in the wing on ascent, and we've got a space shuttle that's in an orbit that can't go lifeboat itself at the space station. And the response to that would be a rescue mission, which was designated STS-400. And that's what I did a lot of work on for about 2.5 years at NASA. And specifically, what I worked on was rendezvous and capture and docking analysis between two space shuttles in orbit. And so you would assume that you would have one orbiter that was the bad one that needed its occupants rescued, and it would have some maybe degraded capability to keep itself in a certain attitude. And then you would have a good orbiter that would come along to rescue the people inside. And you had to come up with a way to do this. And essentially the plan was, the good orbiter would fly up, it would orient itself in a certain position relative to the bad one, and then it would use its robotic arm to reach across and grab the other orbiter. And then through a series of 3 spacewalks, astronauts would shimmy up and down the robotic arm from the bad orbiter to the good one. And there would be some back and forth, and they were going to have to move some equipment back and forth. And, there was this big choreographed spacewalk procedure for these 3 spacewalks, and, who goes where and what equipment and everything. But you would eventually get everybody over into the good shuttle, and then they would just have the bad shuttle pilot itself into the Pacific Ocean and break up on re-entry. It would essentially keep the payload bay doors open and re-enter upside down, so that it would encounter all this turbulence and it would start breaking up at very high altitude, so that by the time it got to low altitude, the pieces would be pretty small, and then they would all fall into the Pacific Ocean, several hundred miles north of Hawaii. And so I guess the assumption is we could at least pressure people not to have their boats out there because it's Hawaii, and I don't know. There would probably be fewer unaccounted for idiots out there in their boats.
Yeah.
And in that analysis, I met Rodney Rocha and kind of worked with him a little bit. So I knew him there. He had an interesting job for STS-400, and I would describe it as, he kind of had a free hand to go around and in a very good and helpful way stick his nose in everything. And NASA, maybe generously and maybe not, said, you were the guy who said this was a problem last time. We didn't listen to you, and 7 astronauts died, and we lost a shuttle. We're going to let you go do anything you want this time. And I can imagine there was probably good sentiment in that order from a lot of people, but I bet there are a lot of people, maybe Linda Ham among them, who would have said, you know what, if this one crashes, we can pin it on Rodney this time.
Maybe so.
So Rodney would come over, and I was doing essentially crew trials. So I had astronaut test subjects who would come in, and you would have a pilot, and then you would have an arm operator, and they would work together on the simulator, and they would fly the simulated shuttle up to the derelict shuttle, and they would use the arm to capture it, and then they would establish the proper station keeping, and I would be taking a bunch of data through the simulation and recording notes and everything else. And basically it was a feasibility study of, can you do this? And then there were other elements that were done offline where I would analyze what was the capability of a good shuttle to maintain the attitude of two shuttles in orbit connected by the robotic arm. And that's kind of a problem because you have these two huge masses, essentially like a giant heavy barbell with huge masses on the end separated by some distance. And they're in orbit, and there's some orbital mechanical effects that make that kind of difficult. And so Rodney Rocha from time to time would come around and see the simulation or sit in on some of the crew trials. And I was kind of wrangled into sitting in on a weekly conference call where this committee was coming up with all these EVA ideas of, which astronaut moves across the arm on which spacewalk and all these things. And really, I didn't have any input into that because I was just a shuttle arm guy and not an EVA guy. But I think they wanted someone from the shuttle arm community there since they were crawling up and down my shuttle arm. And ultimately, they would launch that mission eventually, not STS-400, the rescue mission, but STS-125, the Hubble Space Telescope servicing mission. And there was no real problem. There was a little bit of thermal protective system damage, and they decided it was not an issue. So they didn't launch the rescue mission. And so 2.5 years of work that I did was never used, but such it is in engineering. But ultimately, they seem to have a plan for that and seem to put the right guy in charge in order to learn from their mistakes before. But in the future, will they remember that? At some point, Rodney Rocha has to retire. Maybe he's retired already. I don't know. I searched for him on LinkedIn, but couldn't find him. There are a lot of people who, by the time NASA is launching a vehicle again in the future, they were probably in junior high at the time of Columbia. They might have been younger. They might not have been born. And will they remember those lessons when that time comes? And that's the real danger. It's, we can write reports and we can investigate things and we can write very weighty conclusions on the consequences of our actions as engineers. But ultimately, we have to somehow find a way to pass that stuff along through time and pass that to new engineers. And that seems to be where this breaks down.
I feel like it's because there's a lack of focus on how to structure and incentivize organizations to achieve certain goals. And so the way that NASA is, well, let's start with how it's incentivized. So NASA's biggest incentive, probably, like any large bureaucracy, is to sustain its own existence. That's the most important goal. You don't want to be the person who's in charge of NASA who causes it to lose all of its congressional budget, because then it will cease to exist. And so one of the important things is you need to produce results that get a budget. It's not produce safe manned missions or even missions at all or manned missions or safety. You don't need to do any of that. You have to figure out how to maintain your budget. And so that's really where that incentive is. And then it sort of percolates down and it becomes lost as you go from politician at the top, because the leader of a large organization like that will almost always be someone who's very political in terms of their skill set. And then it'll percolate down to engineers who are trying to get their organization's ostensible job done. Like it'll go to biological life sciences or whatever, and they'll be like, oh, what's really important about this is the plant experiments or something like that. And they'll actually try to achieve their goal because they've completely lost sight of the we have to keep NASA alive goal. And so that's a huge problem. And I don't really see people building organizations where they're like, we're going to pay you for astronauts coming back to the ground alive. Like, that's when you get your money and you don't get it otherwise, or something like that. I know that's hard to build, but no one tries. And then on top of that, no one says, let's structure the organization in such a way where it works like that. I mean, I don't know what that would look like. Do you have an archivist as the most important person in your organization, and their goal is to keep all these memories alive somehow and percolate them down? But the organization is structured where it's just like, let's break it into departments kind of by what they do. And that's not really the best way to preserve lessons. It's not the best way to care about cross-cutting concerns. Like, hey, maybe let's not build a vehicle that can shed foam into its own airstream and damage itself. Like, the rockets that came before and after the shuttle don't have the ability to damage themselves in this way. So, like, how was NASA organized in such a way where they said, yeah, the shuttle, that sounds good, let's build that? So I think those are the major failings. And I feel like when people think of engineering, they don't think of engineering an entire organization for success. And maybe chief engineers who are in charge of 500 people and can reorganize it do think of this, and I'm not giving them enough respect. But judging from what I've seen in the corporate environment and from researching accidents like this, people don't really give it enough thought.
I agree. And you know, in my career, I've seen turnover of vice presidents of engineering and CEOs so often that you cannot have that kind of organizational change in the corporate world. And NASA is even more vulnerable because it is essentially a political organization. It has an administrator, but the administrator is appointed by the president of the United States. And every 4 or 8 years, we get a new president of the United States. And NASA invariably gets an entirely new mission with a new administrator changing things from the top. And so as difficult as this organization built in the way Blake says would be to do in the corporate world, it's even harder at NASA.
Yeah. So I think they'll keep losing manned vehicles if they keep flying them.
Yeah, I agree. And you know, I spoke to that too at the end of the Challenger podcast about the magical thinking that still goes on at NASA about, hey, we have this vehicle that exists on paper and it's 3 times as safe as the shuttle. And you know, what is the rationale for claiming that? Does it have 12 hydraulic systems instead of 4? You know, it's crazy to think we have a notional high level design on a piece of paper and we haven't addressed these organizational issues, but we will now be 3 times as safe.
Yeah.
And I feel like if either of us brought these kind of things up to people in our management chain, we would see a lot of agreement with our direct managers and maybe the director over them. And as we go higher through the management chain and eventually reach vice presidents of engineering and CEOs, they would just consider us troublemakers.
Mm-hmm. They would also be very good at making us feel like our ideas had been heard. And then they would be very good at preventing us from ever accomplishing anything.
I think that's how you become a VP of engineering or CEO.
Yeah. Because you don't get paid directly for success.
Yeah. Unfortunately.
I can think of another side effect that came out of Columbia. You would probably know more about it than I do. But if I recall correctly, on the future missions after Columbia, they brought up, I think, an additional extension to the arm that had a camera at the end of it. And they would do a scan of the entire heat shield of the shuttle. And it added an extra day or maybe an extra 2 days to every mission just to look at it.
Yeah, so they engineered this basically as about a 50-foot long boom, and they would store it on the left side of the payload bay. Now, the space shuttle was originally designed where it could have 2 robotic arms, one on the left and one on the right side of the payload bay. They only ever flew right side arms. They never flew a mission with 2. That we know of. Maybe those DoD missions had to. Who knows? Those secret missions, but none of the available information on the unclassified missions they ever flew to. So what they did is they built this boom and they would just sit it in the cradle that was supposed to hold the left side arm that had basically never been used in the whole shuttle program. And this boom on the end of it had basically a laser scanner thing, and it had a high def camera. And because of the length of the boom and then the reach of the robotic arm could pick up the boom and use it to scan the entire underside of the shuttle. And they would do this on flight day 2 while they were trying to catch up with the space station to rendezvous with it. And then after they left the space station, they would do it again the day before re-entry. And so engineers on the ground, and we would support this, like working in the shuttle arm group when I was there, we would support that activity as they were going through the procedure, doing the scans. And so engineers would be watching while the video image was being downlinked live, and they would just be looking, is there a giant gash in any of the tiles? Do we see any huge holes in the vehicle? But then they would also download the laser scanning data later, and they would have a computer program that would process that. And so it gave a huge amount of fidelity into the state of the tiles, and they could scan the tiles before launch while the vehicle was in the vehicle assembly building, and then scan them again on flight day 2 when they were in orbit, and do a diff between those 2 scans and see if there was any damage. And so it gave them a huge ability to see what potential damage was. There was a later mission after Columbia while this boom was being used, and it was used to the end of the shuttle program. There was a later mission where they did have damage across a couple of tiles. A piece of debris had hit and put a gouge in a couple of tiles. And we went into a meeting the next day, and they had used one of these early, 2007 era 3D printers that used to print in the really bad, expensive waxes and stuff. And they had used one of those to construct a 3D printed version of the tiles, a model of the tiles. And then they had constructed the negative of the void. And so they would fit together, and you could see what the shape was and everything. And they had that in the meeting we went into to discuss whether this damage was important or not.
Why would they scan the shuttle before re-entry?
In case there was any micrometeorite damage that had been sustained while it was at the space station.
Okay. And then you would scan it before, on day 2, because you were deciding whether or not to use the station as a lifeboat?
Yes. That decision had a little bit of time constraint on it. Not a ton. They needed to go ahead and do it and just clear the rest of, clear the orbiter's health so they could get on with the rest of the mission at the space station. But they did also need to go ahead and hurry up about getting the other orbiter up to rescue them if there had been a problem. They didn't have unlimited time. They had a lot of time, but they still needed to move a little quickly. I mean, the space shuttle in orbit had something like a variable 25 to 40 day life in orbit because of the fuel cells it used, depending on whether the extended duration orbiter module was installed in the payload bay. So, it could last about a month in orbit, but eventually you needed, if it was unlandable, if it would not survive re-entry due to damage, you eventually needed to get rid of it and get it off the space station because you didn't want a dead orbiter hanging there on the side of the space station. Mm. One interesting thing I learned during my research for this was that part of the post-Columbia changes was they gave the ability to remotely lower the landing gear on the orbit.
Why?
That was something that had not been possible. The shuttle was always remotely pilotable from the ground, but up until the post-Columbia era, there was no way to lower the landing gear. And I guess Blake has a more interesting way of explaining why.
Oh, yeah. It's because the astronauts wanted to ensure that they would be necessary to fly the shuttle. And so they made it so that, or they insisted that it was dangerous if any automated system was in control of the landing gear, because it could always just accidentally pop the landing gear out while they were still, say, high up in the atmosphere going Mach whatever. And so they're like, we should be in manual control of that. thus ensuring that they would always have a job and no one would just be remotely piloting shuttles to orbit and back.
Yeah, and obviously the flaw with that argument is if the computer is flying your shuttle, it can screw up all kinds of things catastrophically, not just the landing gear. Mm-hmm. So after Columbia, they engineered basically a cable that would connect with a data receiver computer on the mid deck, and then it would connect that up to the flight deck. It was like this 25-foot long cable. So it would send those last couple of signals, and there were actually like 8 signals that could not originally be sent that were required. So then they could do all the piloting from the ground. Now, that was going to be used. They never intended to actually send an unmanned shuttle anywhere, except in the case of irreparable thermal protection system damage requiring them to discard a shuttle. So the idea there would have been the astronauts have taken refuge on the space station. They do an automated undocking of the shuttle from the space station, and then they basically fly it away from the station a good ways. They open the payload bay doors, or they'd be open already, and then they just turn belly up, so they're the payload bay facing the Earth, and then they do their deorbit burn, and they turn back around to have nose forward going into the atmosphere, and then all the turbulence would burn them up. But they would be capable of doing that remotely now.
And I guess they would pop the landing gear out to increase the turbulence?
Sure, why not?
I mean, is that what the point of that was?
I think the whole point was they had other signals that had not been available before that they needed. And they were like, let's just add them all. All these astronauts will be out of work in a few years anyway.
They'll never work again.
The astronaut jobs program argument no longer works. Do you know a poor unemployed astronaut who needs a job? I considered trying to contact Rodney Rocha and being like, hey, we worked together like a tiny, tiny bit about 10 years ago. You want to come on our podcast? And then I was like, nah, he would probably like look us up and he'd see how much we like shit on NASA. So I don't think he'd do it. Plus, there's almost no chance that he would remember me.
Maybe you could send him the episode.
He'll probably get a hold of it one day. Somebody will send it to him.